Hi, I'm Gregory Ramsey. I am in the Information Science and Systems Department in the Earl G. Graves School of Business and Management at Morgan State University. I do research that relates to computational modeling, simulation, those sorts of things. And I'm always interested in knowing better ways of being able to do simulations. And that's one of the things that's gotten me interested in quantum. Also, I have an interest in how we are going to prepare our students for the future.
Sure. My name is Birol Öztürk. I'm an associate professor of physics in the School of Computer, Math, and Natural Sciences at Morgan State University. My research is on using defects in wide bandgap semiconductors for quantum sensing. So, as you mentioned, simulations are related to quantum science. My research will not help you, most likely, because it's mostly quantum sensing. But you can use the same materials, the hardware, same hardware, for building quantum computers. And that will be actually the hardware that you will need for those simulations, quantum simulations also, you can call them.
Okay. So when you say you're looking at defects in semiconductors, what is it that you're interested in doing? Trapping electrons or trying to find out how many have been caught in a lattice? Or, I mean, kind of give me a little bit more on that.
Sure. That's a good question. So about 20 years ago, I would say, we realized that physicists or scientists realized that you can use defects in diamond for quantum applications. So it has quantum properties. So when I say diamond, I'm actually talking about pink diamond, the pink colored diamond.
Okay.
So it turns out the pink color, so diamond is naturally transparent. Good quality diamond without defects. It's all carbon. It's, as you know, it's transparent. But the pink diamond has the pink color because it has actually nitrogen instead of, in certain places, it has nitrogen atom instead of carbon. So when nitrogen is in there, it doesn't fit into the place of carbon, but also we have to take out a carbon. So it's, instead of 2 carbon atoms, you have 1 nitrogen atom and also 1 defect, so it's a vacancy. So 1 carbon atom is out. So if you have this configuration, it turns out the diamond will be pink. So in our experiments, we send green laser, and we get this red color back. So that's why you see it pink color. So this configuration of atoms in the diamond has quantum properties such that it actually interacts with external magnetic fields, electric fields. So, scientists realize that it is so sensitive that you can actually use it as a sensor, right? So you are looking at this optical signal, like the red color coming from the diamond, and if there are magnetic fields, electric fields around, you will see the change in intensity. So this is actually called NV, like nitrogen vacancy, NV color centers in diamond. So diamond is not a conventional semiconductor, but it has a band gap, and so it does fit the description of wide band gap semiconductors. And later on, actually more recently, we realized that what's happening in diamond with these NV color centers can also happen in other materials, like silicon carbide, for example. So silicon carbide is well known in the industry. It is used for different applications. But so far, we have been trying to avoid those defects. So we were trying to make materials without defects. But with this new approach to science, now we want those defects, specific defects, because they are excellent sensors. So we are trying to leverage this property of those defects to build next generation, very sensitive sensors for sensing magnetic fields, electric fields, temperature, the microstructural defect, like deformations, like strain on the sample. So it is exciting. There are actually already commercial products based on this technology.
Okay.
You can buy them. So it is probably one of the first products of this new quantum era. So the quantum computers are being built, but they're still being tested. You can't buy. I mean, one company sells a quantum computer, but its performance is questionable. Mm-hmm. But this sensor you can actually buy, and it works. One important advantage of using defects compared to other technologies. So I didn't explain it, but as you might know, one thing you mentioned, like trapping atoms, is one approach. Or those companies like Google, IBM, they are mostly using this other technology called superconducting qubits. Mm-hmm. So those technologies require actually cold temperatures to work, very sophisticated equipment, and very cold temperatures. But the advantage of defects is that they actually work at room temperature. So it's a big advantage.
Okay.
So you don't need that expensive like helium gas, the cryogenics. So the defects can work at room temperature. So that's the biggest advantage.
What's the potential for miniaturization? Because when I see these pictures of quantum computers, they're huge things, and then of course the cryogenics that have to go around it.
Exactly.
It's really big. So if you're talking about something that can operate at room temperature,
Mm-hmm.
then I imagine that the potential for miniaturization does exist. Is that
Yes,
true?
exactly. If you can do it at room temperature, the commercial device, if you check its images, it's like a tabletop small instrument because it works at room temperature. You don't need the cryogenics, large room, the vibration is not as big as an issue, mm-hmm. things of that nature. So it definitely has that advantage. So it does have disadvantages, my approach. So for example, when you trap atoms, you're just working with a single atom. So there is nothing around it. There is no interaction with neighboring elements, atoms. But again, to get this, you have to have like good vacuum and everything to get everything else out. But when you work with defects, you know, it's a host of material. There are a bunch of atoms around and other defects around that may affect the performance.
Okay.
So, I mean, there are disadvantages of this approach. But these are all, you know, going in parallel. So we don't know who is a winner.
Right.
So there are different approaches, which is, I think, good. People are trying, scientists are trying different approaches to get there. There's no clear winner at this point. And I guess we'll see. It's a very fast moving field. We are hearing things, as you know, every other month, like some new development. So I think we'll find out maybe soon.
Okay.
The winner is.
When we talk about quantum, oftentimes people think math. I can't do this. This is too much. Right? And one of the challenges that I'm faced with is I go into the classroom, I want to be able to communicate to the students that this is something that is approachable. This is something that you can learn. And so one of the questions I have for you is, how do we make this topic, this subject area, something that students can tap into, can relate to, can understand, coming from where their background, coming from what they already know? Is there a way that we can bridge that gap?
Yes. So this is very important. So definitely there's a gap there for educating everybody on this topic. So as you know from popular culture, when you say quantum, oh, this is above my level. I can't comprehend this. It actually has been taught that way, even to us physicists. So that is the class that you take in your senior level. You can only start learning after you learn so much math.
Right.
And actually, until so far, it stayed as like a theory class. Like you just learn those equations and sophisticated math, and then no application. So only like few groups were doing the experimental quantum work. Mm-hmm. But it is changing. Now we need people who understands the quantum, not necessarily just the math, and also do the work, the actual work, right? So, for example, a big part of this quantum systems is radio frequency signals. So in most of these approaches, we use radio frequency signals. And it's actually was a, I would say, subfield in electrical engineering. Mm-hmm. And it was a field that was dying. It wasn't very popular anymore. But now it's coming back. We need those engineers who understand those. So not all the physicists work with radio frequency waves. So, and most of these technologies that we are talking, they are very interdisciplinary. Right. So we have to mention that. They are very interdisciplinary. They require people with backgrounds with physics, engineering, computer science, and then there's actually even the business aspect, right? Like you want to sell these products. So
actually apply the products.
Apply the products,
in commercial ventures.
Exactly, exactly.
So that's where I'm coming from and what I'm thinking about.
Sure.
How do I teach students the importance of quantum, how to use quantum, and that they can relate to quantum?
Yes.
Right? That's what I'm interested in being able to do.
Sure. I think all the fields now should start thinking about this.
Right.
How do I incorporate quantum into our curriculum? That's a major task, and it's very important. So I think we can mention our NSF Convergence Grant.
Yes.
So that we recently finished phase 1 and trying to get the second phase. So that's one way of doing it. So you fund this kind of project, so people get together, brainstorm, and then find ways and talk to professionals, include professionals, and find ways to teach these complicated concepts at a level that's good enough for that particular major.
Right.
So you don't need to teach apparently
Schrodinger equations.
Yeah, like a sociology major, for example, to solve this complicated equations. But they can be quantum literate. They can understand the basic concepts, what you need for what product, or whatever applies to their field. They can understand those basics. They should be able to understand those basics. So, it's a big race now.
Right.
A lot of nations are trying to get this first. Europe, Asia. So, and you can't do this without the required workforce. You definitely need it. It's not a question. And unfortunately, there's a gap also there. We don't have the required workforce. So we need more people trained on this, more students, the general public, more understanding of it. So it's a must that we should focus on this issue right now, and start finding ways to train everybody, but only as much as they need. So we don't want to obviously teach everybody those sophisticated equations.
So as we start talking about training people, then that means we have to train the trainers.
Exactly.
Right, and that's going to be a really important thing. So when we go into a business environment, or even if within my field, like in information systems, the professors who are teaching the classes need to understand what are the basics of quantum and how does it relate to each of the topics that we cover. It could be on the database. It could be in programming. Speaking of programming, how you program a quantum computer versus a conventional or classical computer, it's different. So
it is different.
That requires a different way of thinking, and introducing that way of thinking to people is something that we need time for, right? We need time in order to pick up the new paradigms and to be able to incorporate them. And one of the techniques that might be helpful for us is to figure out modules that we can introduce into classes where we're just giving people a taste, but whetting their appetite and letting them see what's the potential of this.
Exactly. This is very critical. You brought up the computing part. Yes, it's an ongoing research.
Right.
It's critical, and we already have prototype quantum computers. And researchers can actually work on them. And they can actually develop algorithms and actually run simulations. So it is available now. And we have to be ready to actually make this at a large scale. There are few prototypes available, but it's coming. You know, the companies are investing a lot. The world is investing on it. So we have to be at the front of things. Like, we have to make sure that we are in the race and we are training students accordingly. They need to understand the basic concepts of quantum, and then this difference you mentioned. It is different. The algorithms are different. It doesn't work as the same way as we program our classical computers. The students should start understanding how to do it. Like the algorithms, programming a quantum computer, how to use it. And actually, we are talking about quantum computing, but then the communication also needs programming. So we need students to understand that part as well. So it is critical, and we put it very nicely. We should start by maybe including some modules, and then maybe convert it into classes, to degrees, certificate programs. So everything should be considered.
Well, we have enjoyed having an opportunity to talk.
Same
and
here.
I think it's been very informative.
Thank you.
So, you know, thanks for answering some questions and
Thank
talking
you.
with me.
Thank you.
All right.